Is my sound okay? Is it too loud? Good? Okay. So let's see if I can get my slides up. All right, great. Hello, everyone. It's an honor to be here today. My name's Lee. I come from New York. For the past 2 days, I have heard a lot of great stories, great presentations about databases. And honestly, I've learned tons about databases myself for the past 2 days. However, today my talk is not about database. Today I'm going to try to change the taste here. I'm going to tell something about how to efficiently manage your cluster resource using 2 very interesting technology here, Mesos and Cook. Okay, so before we start, just a little bit about myself. I am a software engineer working at 2 Sigma. 2 Sigma is a quantitative hedge fund based in New York City. It is a technology company, really. We apply math, computer science, and engineering just in the field of finance to provide values for our customers. So I promise Martin I won't talk too much about 2 Sigma, and that will be it. So let's get to the cool stuff. What are we going to talk about here? We're going to talk about Cook and Mesos. So what are those? First of all, I'm going to give a quick introduction to Mesos and Cook, and to try to make sense why it's interesting. So Mesos is an open source Apache project. It is created in 2010 in UC Berkeley, and by 2012, Mesos has been used by Twitter and Airbnb, 2 very large companies, in their production system to manage their cluster. And this year, in 2015, Mesos has been used by many, many more other companies, including Apple, Bloomberg, Cisco, eBay, Yelp, all these big internet companies. So what does Mesos do exactly? So Mesos is a great tool to build distributed applications. Well, here by distributed applications, I mean an application needs to launch and manage remote process. It can be a compute framework like Hadoop or Spark, or it can also be a distributed storage system such as Cassandra, Kafka, and React. So before I talk about why Mesos is great for building these kind of things, I want to first think about what's common among them, what's the commonality among all these systems. I think there are 3 things. The first is all these applications, they need to manage resources, CPU, memory, disk. Because they're running this remote process on a set of worker node, they have to know, well, what are the available resources? Otherwise, they will end up overloading the machine. And also, for a system like Hadoop Spark, and because they're running user code, they have to make sure it implements resource isolation to make sure those remote processes, they don't affect each other, they don't step on each other. The second thing is, these applications need to manage the life cycle of those remote processes. They need to know when a process starts, when they complete the OK, and when they fail. This might sound easier, but if you think about this in a distributed environment, if you think about all the cases of network partition, I mean, hosts can disappear, hosts can be overloaded and not responding. If you think about all these, this does not become trivial anymore. And thirdly, they all need to manage communication somehow between the master servers and the workers. Because they're sending requests to the workers, I mean, it doesn't matter if you're using messaging queue, HTTP, or any kind of RPC. The point is, you have to have something that you need to manage yourself. So now let's see why Mesos is great, why Mesos can help with all those 3 things I just talked about. So here is just a quick example of an application here. I take Hadoop as an example, and on the right side is the Mesos system. So Mesos runs on top of your physical machine or a virtual machine and provides this abstraction layer of your underlying nodes. You don't see machines anymore. Instead, Mesos abstract those machines into this idea of resources. So basically, it will send so-called resource offers to the applications. In this case, Mesos is going to tell Hadoop saying, okay, I have a CPU and 128 gigs of RAM. Do you have something to run? Do you want to use it? Well, in this case, the application can say, well, yes, I want to take them and run this setup process. Or the application can decline saying, well, I don't need this at this moment. So in this example, let's just say, well, Hadoop choose to run 8 mapper, each with 1 CPU and 16 gigabytes of memory. And Mesos can say, okay, I'm going to do it. And once they finish, Mesos is going to send back a status update saying, well, they finished. And because of those resources has been freed, Mesos is going to send the same resource again to the applications, and so on and so forth. So this is a super simple example, but what does it tell us? What does it solve the problem we've just talked about? Well, the first thing is resource management. So here, because of the idea of resource offer and the abstraction, the application here does not need to worry about what's available anymore, because Mesos will do the accounting and offer what's available to you automatically. Also, here, when Hadoop launches the setup the process, Mesos will set up the containers and do isolation for you automatically, and without even you saying so. So in this case, Mesos will make sure those mappers don't use more than 1 CPU and 16 gigabytes of memory. The next thing here is lifecycle management. Well, it's pretty easy here as well. Mesos is simply going to send you all the status updates for all the status changes to your underlying process. If they fail, Mesos is going to say it failed. If it starts to run or completed okay, Mesos is going to say that as well. So that's taken care of. And also, communication is taken care of as well. It's not shown in the graph, but Hadoop in this case only needs to talk to this driver library that's living inside the application process. So there's no network traffic. All the network traffic is handled inside Mesos. Mesos implement this reliable messaging protocol inside, and it will deliver your message as reliable as possible without you worrying about that. So now, because of that, the application developer does not need to worry about all those things. They can be lifted from the burden of dealing with all the nitty-gritties of distributed system, and instead, they can focus on what's the most interesting thing, which is the high-level application logic. So before I continue, I just want to define a few of Mesos primitives here, which I will be using for the rest of my talk. So the distributed application in Mesos terms is called a framework. So Mesos can support multiple frameworks running on top of the same cluster, which is also a great feature. The second thing is available nodes, available resources inside the cluster is called resource offers. And the framework can take these offers and launch task. So that's the 3 things we will be using. So this is how Mesos look in 2 Sigma. So at 2 Sigma, we use this Mesos to manage the majority of our compute cluster, and we run a single framework on top of that called Cook. And for the rest of my talk, I'll be mostly focusing on Cook because I think it's very interesting. So what is Cook? Cook is 2 Sigma's simulation platform. Well, let's not worry about what simulation right now, but Cook manages tens of thousands of simulations every day. And also, Cook is responsible for sharing compute resources among all its users, because we have a lot of users and only one compute cluster. So what is simulation? Simulation is nothing special. Simulation is just a idempotent, distributed, resource-intensive computations. It can be similar to a data processing job or a ETL or anything machine learning. It's just a simple compute workload. And people rarely just run one simulations. People run simulation in a batch fashion. They run a simulation set anywhere from a handful to 1,000 pieces of simulations. And one simulation is broken down into multiple Mesos tasks to improve parallelism. A simulation task can usually take 10 to 100 gigabytes of RAM, and it can take from 1 to 20 CPUs, and they can run anywhere from 15 minutes to a few hours. And we have mainly two simulation use cases here. The first one is interactive. So in this case, the simulation set, they are much, much smaller, and they're very latency sensitive. So in this case, user will be actively waiting on the results of those simulations to decide what to do next. And the second use case is called batch processing. In this case, the simulation workload is much, much bigger, and latency isn't a great deal here because people don't care about the results as long as they finished overnight, over a weekend, or over the course of a couple of days. So these are the main difference, latency sensitive versus latency insensitive. So what is our problem here? In Cook, we face a problem, which is we face a very high resource demand. So at peak hours, the resource demand we are seeing, they can be 5 times the capacity or even higher. And because of that, Cook is really trying to optimize for two things. The first is utilization. And because we have such high demand, we want to make sure we utilize our cluster as much as possible. And so we can process the workload as fast as possible. The second thing is fairness. Again, because Cook is a shared platform, we want to make sure Cook allocates resources fairly to all of his users due to some definition of fair. Well, I think utilization here is pretty straightforward, but fairness is a little bit tricky to think about. And why is that? So what is fairness? Well, there's a lot of definition of fairness, and there's a lot of ways to achieve fairness. Here's some example of fairness I've come up with. First come, first serve is a way to achieve fairness that we use in our everyday life. When we go to a store, we go to a restaurant, we go to some service, it's usually first come, first serve. So maybe we can use the same idea for our resource sharing. Or maybe we can do time sharing. Let's say if we have 24 researchers sharing the cluster, we can say, well, each one of them can get 1 hour every day. Or we can throw a dice at the beginning of the day and decide who's going to use the cluster for the rest of the day. Well, these are all reasonable definitions of fairness in my mind, but the question I want to ask here is, are they useful? Do they help our use case? Well, to illustrate that, let me tell a story of a simulation user at 2 Sigma. So imagine you being a simulation user at 2 Sigma. One day you have this idea that you have this idea to predict, let's say, the stock price of Google, and you want to try it out. You want to implement a program and to see if it actually does what you think it will do. To implement your program, you want to run simulations to test that. You want to run simulations for the past 10 years to see if your assumption is correct. So to do that, you submit a set of simulations. They're pretty small, they're pretty fast, because you don't want to waste too much time. You know they normally finish in 30 minutes, so you go to lunch, you get a very great lunch, you got fully energized, and you sit down ready to analyze the result. However, at which point you realized, well, your results has not come back yet. They are still waiting for scheduling, they're still sitting in the queue waiting for resources. And now you're kind of upset because you don't know what to do. You have to sit there and waiting and wasting your time and company's money. Well, however, what makes you more upset is when you look at the cluster utilization, you see yourself only using a tiny bit of it while other users are using much, much more. Well, now you're really mad. You say, well, this is crazy. I have to talk to someone. This is absolutely not fair. So what does this story tell us? What I'm trying to say with that story? What I'm trying to say with that story is fairness is not really about fair. If we think back in the story again, the user will not need to look at the resource distribution in the first place if he gets his results back in time. So what is fairness about? Well, fairness is really about user experience. The fairness we want to achieve is a way to provide better user experience, which means the user should get their share of the cluster whenever they need it to do the work they want to do. Okay, so just a quick recap. So far we talked about what is a quick introduction to Mesos and Cook. We talked about our problem, utilization, and fairness. and we have some ideas about what is fairness. So how do we do it? How do we achieve the fairness we want to achieve? Well, the first idea is really simple. It's called static quota. So quota is basically the max percentage of cluster usage allowed for a single user. Well, in this case, first we just calculate statically. We estimate what's the max number of concurrent users we are going to see in the system, and we simply divided our cluster by that. Well, it has a clear benefit. It has a great fairness because we're essentially reserving those resources ready for the users to use at any time. Well, however, the problem is also pretty straightforward. It leads to poor utilization. I mean, during daytime, we can still have 95 or even 100%, close to 100% utilization. However, during night, because of there are much fewer users and much fewer interactive research, the utilization drops to 30, 40%, while there's a lot of big batch processing jobs bounded by their quota and waiting for scheduling. So this is not great. What can we do? What can we do better? Well, the next natural idea is to adjust the quota. Basically, when the utilization is low, we want to increase the quota and vice versa. Well, the benefit of that is also it leads to high utilization. During night, we can have utilization of 70, 80%, and we're quite happy about that by using this approach. However, the problem is it leads to poor utilization again. And the reason for that is even though our quota can adjust rapidly according to utilization, the allocation cannot. It sometimes takes us hours to go from the left side to the right side. And that is because, like I mentioned earlier, some of the simulation tasks, they can take hours to run. And once those takes the chunks of memory, you will have hours to reallocate. So can we do better? Static quota is great in fairness and low in utilization. Dynamic quota is the opposite. Can we have something that's both high in fairness and high in utilization? Well, the next thing we tried is called preemption. Preemption, it simply means to kill a simulation task and to reschedule it later. The key point of preemption is it is a fast way to reclaim resources. And therefore, instead of taking hours, if we use preemption to reclaim those resources actively, it only takes us minutes instead of hours to go from the left to the right side allocation. So this is great. This is going to be much, much better. So how do we do it? How do we implement preemption? So let's start from intuition. Let's see what's the idea behind preemption. So here's a quick example here. Let's say we have a cluster of 6 CPUs. We have 2 users here, Jerry and Calvin. Each of them are running 3 tasks. Each task, which is a blue box here, represents 1 CPU. So they're happily sharing the cluster. Everything is great. Well, now comes a 3rd user, Dave. Dave wants to run another set of 3 tasks. And now at this point, we no longer have a fair allocation. Well, we know eventually we want the cluster to look like this. We want each one of the users to having 2 tasks running. However, the problem is we don't know how do we choose which task to preempt. Well, one thing we do know is we do know Jerry and Calvin, they are all above their fair share, so we can preempt either one of them. But because we don't know anything better at this point, let's just say we pick one. And we do that, and when we schedule the next job, same thing here. Only Calvin is above the fair share in this case, so we only preempt Calvin's, which is the red box here, and oops. And we do that, and we end up like this. Well, this looks pretty similar to the allocation we want to achieve, so we're quite happy. Well, however, our users are not happy about this at all. The reason is, what's the reason? The reason is we have ignored a simple fact that not all tasks are equal. And we might have just preempted some very important task. And this leads to terrible user experience, and this is what we are trying to prevent in the first place. So we have to do something better. So the next natural idea is, yes, let's use a score function to reflect a text value, right? a task value should really be two things. The first is fairness. Because we want to achieve fairness, the task's value should represent fairness somehow. And the second thing here is the importance, or the relative importance of task to the user. And our preemption principle should be, well, to simply preempt low-score task for high-score task. So to use the same example here and apply our idea of score function. Let's say here, let's assume each user has an idea of how to order his own task. So I represent a task's importance by currency here. The more currency there is, the more important the task is. One thing to note is that I'm using different currency signs for each user, and that is because we cannot compare among them. We cannot say, well, Jerry, your task is less equal than Calvin's, because we just cannot do that. However, one thing we can do is we can apply our notion of fairness. We're going to say, well, now I'm going to fair, and I'm going to say the most important task of all users are of the same value, and the second most important task of the users are of the same value, and so on and so forth. So we unify the currency in the previous slide into this slide. So now we have a total order of all the tasks waiting and running in the system. Now we can compare them. And to do preemption, well, we just consider a running task that is lower score than the waiting task for our preemption. And one thing to mention here is the reason that we have to look at multiple ones instead of just picking the lowest scored one is because we have to do preemption with the constraint of bin packing. We have to make sure after the preemption, the waiting task can be fit on the host. So here, because in this example, everything is one CPU, so things are quite simple here. We pick the lowest score, we schedule that, and we do the same thing again. And this time, there's only one candidate, there's only one task lower than this waiting task, and we do that. So we end up like this, and we revert it back to the user importance notion. So here, two things. First, we have reached the allocation we want to reach in the first place. And second, we are running the most important task for all the users. So this is great. This is exactly what we want to do. And next, I'm just going to talk about formalization. How do we actually put this into math and computer and programs? So we introduced this notion of cumulative resource share, or CRS in short. The idea is the same as I just described, assuming there's a total order of tasks for each user, where greater means more important than. Now the CRS of a task T is the sum of the tasks of the same user that are greater or equal to T divided by the total cluster resource. Or in mathematical form, it looks like that. So let's go through a quick example to see how that makes sense. So same example here, we just take one user in this case. There's 3 tasks, A, B, and C. Each one of them taking one CPU. A is more important than B. B is more important than C. So the CRS of A is simply what? The resource of A divided by the total resource, because there's nothing more important than it, which ends up being 1/6. And the CRS B is the resource of A and B divided by the total resource, because A is more important than B. And C is similar. So we end up like these 3 scores. So just quickly, same example here. Now we're going to use CRS. One thing to note is the higher the CRS is, the less important a task is. So it's kind of a little bit reversed. So let's say here we do the same thing. We're trying to find a task with higher CRS to preempt. We do the thing. We do that again. We end up running the task with the lowest CRS. So multiple resource, how do we do that? So far, I've only talked about how to handle one types of resources. However, in reality, we have at least CPU and memory to worry about. Maybe something something else as well. So luckily, there has already been work done for that exact problem. It's a paper published, not surprisingly, by UC Berkeley as well in 2011, actually by the same folks that published the Mesos paper. they introduced this notion of dominant resource share, which is a fair allocation of multiple resource types. I'm not going to go to the details of this paper. The notion is very simple, but it has very great properties. So if you're interested, I really suggest you look it up and read it. It's really very well written. So we combine this dominant idea into our definition of CRS. Again, to recap, this is the definition of CRS. And what does dominant mean? Dominant simply means we calculate CRS for all the resource types and we take the max of it. Simple enough, but again, has really nice properties. So if the CRS of CPU of user A is 20%, the memory of user A is 30%, the DCRS is going to end up being 30%. So just the max. So finally, we define our score function to be what? To be just the negate of DCRS, because again, we want the high score to be high importance, and the high DCRS means less importance, so we just simply negate that. So that's the formalization of our score function. So we have a score function now. Let's see how do we put it back together into Cook and Mesos into our system. So here is a architecture of Cook and Mesos. So Mesos we just treat it as a black box. And on the left side, there's Cook. And Cook has mostly 3 components. The first component is called ranker. So the function of ranker is to take the list of tasks running and waiting and calculate the score for them and output them in a sorted order by their score. So the score task list is then feed into 2 components. The first is called matcher. The matcher takes all the waiting tasks and match them with the resource offers coming from Mesos. It tries to launch the high score task first, of course. The second component here is called the rebalancer. The rebalancer is the module that does the preemption algorithm we've just talked about. The rebalancer takes the total, the list, it breaks it down into waiting and running. So similar to the matcher, it does a matching process, but unlike the matcher, it's matching the waiting task with the running task. So it's using running task as another way of resources, and it tries to optimize for the total score. One thing to mention here is because the rebalancer only, one thing to mention here is only the matcher can actually launch a task, and the rebalancer can only preempt a task due to the limitation of Mesos API. So this is a approximation. So rebalancer will only do the preemption part, and when the resource freed, it will be feed back to the matcher, and the matcher will use them correctly for the high score task. So that's the idea behind all these. So we asked the question before of, are we doing better? Now I think it's time that we try to answer it. So to answer that, we did a benchmark. So the benchmark is simulated. So we implement both the dynamic quota and the preemption algorithm in our simulator. We take a 7-day production workload trace from our system and replay it through the simulator to see what's the performance. So again, the 2 things we really want to achieve here is first utilization, and second, fairness. But what is really fairness? Fairness is user experience, right? So we want to have a better metrics on user experience, and we want to have a better metrics or reasonable metrics on utilization. So the first metrics is about user experience. It's about fairness. How do we measure that? Well, the user cares about the time between the submission time and the completion time of the total simulation set. That's basically the latency of the workload. And now we do a pairwise comparison. So for all the simulation set in our benchmark, we take a pairwise comparison of the running time between preemption and dynamic quota. So we used dynamic quota as a baseline here. So the higher score means faster in the preemption case, and the lower value here means slower in the preemption case, just in case. So here, as we can see in the middle, about 60% of the simulation set, they're actually identical. They perform exactly the same in these 2 algorithms. And on the left side, there's about 10% of the simulation set, they actually suffers from the preemption case. They run lower. they run slower. The reason for that is because those are big batch processing simulation sets that goes across over the night. And in the dynamic caller case, if you still remember, they grab the chunk of resource and they hold on to it until they complete. And that's why they run faster. And in the preemption case, they try to do that, but gets preempted when more users gets in and requires more resources. What's most interesting is on the right-hand side, which is the speed up. So about 30% of our simulation set, we see a speed up. And those are mostly interactive, latency-sensitive simulation sets. And the speed up here is really critical for our user experience. And that's why we're quite happy about the results. We think the sacrifice of those 10% batch processing is worth the speed up of those interactive research. The next thing I want to show here is utilization. Well, we don't care about pure utilization. We only care about effective utilization. What is that? What is effective? The idea is we're only counting a task in the utilization if it's not being preempted in the future. So if a task is preempted, it provides no effective utilization for us. So here again, the red line is a preemption. As I mentioned, dynamic code is really great in utilization, so we cannot beat that. Every time we preempt, we lose effective utilization. However, as we might have noted here, those values, when a cluster are of lower utilization, those are in during night, and those are for big batch processing. So the utilization isn't that critical there because we don't lose latency. And on average, there's only about 2 to 3% utilization difference between these two cases, and we think it's a good trade-off from those 2 to 3 utilization penalty to the speed up we are seeing for a lot of our interactive use cases. So I think it works. We think it works, and that's why I'm very happy to share the journey with you, to share our experience with you. And finally, all I have talked about, they are all open source. Mesos and Cook, you can download them today. You can run them in your system today. We are super excited about the results. Mesos has been in production for over 3 years, and Cook has been running in the production of at 2 Sigma for over a year, and we consider it to be pretty stable. And if you're interested in it, take a look. If you have any questions, you can ask me through Twitter or through GitHub. My username is iSilos. Talk to me if you're interested. So with that, I'm going to end my talk and open to any questions. Thank you very much.
Hello.
Hello.
So can you tell us about the problems that you have with Mesos in production during these 3 years?
Can you repeat the question again?
Can you tell us about the problems that you had with Mesos in production?
In Mesos, using Mesos in production?
Yes.
Well, interesting you asked. I was just attending the Mesos conference earlier this year, and the same question gets asked over and over again. The answer is, from our observation, Mesos is super stable. We have no failures with that is contributed to Mesos, and other companies seem to share the same feedback. So I think Mesos is pretty solid as a product. I think Twitter is running ahead of Mesos in the production system, and other people are just using stable releases. So does that answer the question? Sure. The gentleman over there, please.
Hello. Thank
Hello.
you for your talk. I think the most unclear part is how do the cook assign the scores to the tasks? As far as I understand, it is assigned automatically, yes? So could you please describe the principles of this automatic assignment?
So the question is, how does Cook assign scores to these tasks?
Yes.
So I think maybe you mean like the user, how do users define how the importance of this task is? Is that your
So
question?
it depends on how did the user define the
Right,
importance, yes? But naturally, every user will define his task as a very high important.
Well, right. The point here is even if they do so, the importance is relative. So it doesn't matter. You can say your task is super important, but that only matters within your own domain. It does not affect the CRS, how score function is computed for other users. So that's like one key point. So you can say the importance that the user specified only matters within the same user. So the user has no control over how Cook assigns scores to other users. Does that answer your question?
Yes, thank you.
Yeah. Just as a side note, by default, each user will assume earlier submitted task is more important than later submitted task, unless they specify otherwise. So that's kind of default behavior.
Hello, can I ask a question? Here I am. Hey.
Sorry. Yeah, please.
Oh, sorry.
Sorry. I'll go there later, please.
Oh, okay, thank you. I have two questions. They are about the rebuilder and the matcher. The
Okay.
rebalancer and the matcher.
Right.
First of all, could you tell something about migration of the tasks? So, as I understand, the rebalancing means only to kill the task and to match them again.
Right.
But have you any plans to make some sort of live migration or migration of already deployed tasks, for example, from one resources to another? And the second part of the question, could we make a larger matcher for already deployed tasks? For example, if we first of all need 2 CPUs, can we make 4 CPUs for the same task that already deployed? Thank you.
Let me try to make clear the question. So the first question is if we can do some checkpointing. Is that what you mean too? Okay. The second question, can we over provision the resource?
Yeah, over provision, yeah, of course.
Okay. So for the first question, that really depends on your workload. If your workload supports checkpointing, what's going to happen is when a task being preempted, it will checkpoint its state, and when it gets relaunched, they can pick up from the state. If you like send a state in some database or somewhere, so it's like automatically handled if you have a restartable workload. The second question is about over provisioning. I don't really understand why do you want to do that, because there's a feature. Actually, there's a feature in Mesos. If you have 20 CPUs. The assumption will be if you request for 2 CPU, you're likely be not using 2 at the same all the time. So it will like lie to the framework saying I have 40 instead, and do some handling underneath. So it's like over subscription for VMs, similar to the idea. So I don't know if that's something related to your question or.
For example, we can need additional resources if the user tells us, okay, I'm going to do some simulation and I need as much resources as possible, or he couldn't.
No, the user cannot specify crazy, because the assumption will be the user will specify the resource reasonably, and actually we have a system to actually automatically estimate the resource for them. So the end user don't not need to do that. We have a middle layer to do some learning and to find out what's the CPU and memory usage likely to be for those simulations. So yeah, I think other users can do similar.
Thank you.
I'm going to go to this side right now.
Hi.
Hello.
Thanks for the great talk.
Thank you.
As you already said, Mesos and Cook allows to more effectively use resources, but is there any overhead of using Mesos and Cook itself, like allocating resources takes time, takes CPU and so on? Is there
A
some
plan to do what, sorry?
percentage? Like planning tasks takes time too, and takes some resources to reallocate and so on. And compared to task execution, what is the overhead?
In our use case, like I mentioned, our task, they run 15 minutes at minimum, so we can actually afford some latency in the scheduling. But in some kind, if you have other use cases, the scheduling time might actually be a problem for you. So you might need to like have a session or have a daemon running that taking up those requests instead of like launching a thing that's gonna live for a second. So And Mesos actually pretty fast, but Cook isn't really designed for this kind of high frequency cases. Mesos, I think the latency is maybe a few seconds. So, I think I can take one more,
Thank you.
please. Sorry.
Hello.
Oh, okay.
Thank you for lecture. In continue for last question, in last benchmark you mentioned that utilization is for dynamic preemption preemption is about 90% of resources, and last 10% which you theoretically lose. It is about initialization of task, it's about measures, it's about cook, or where you lose this 10% of resources.
Sorry, I don't really understand.
Please open last benchmark slide.
Can we turn the slide back? Yeah, I think it's the next one. Yeah, we can take this offline. I think I'm running out of time. Can we talk offline? All right.
Okay.
Thank you very much for your time, and again, thank you for having me here.